Hey guys, what's up? My name is Gabe and this is Games with Gabe. This is the next episode in the Coding a 2D Physics Engine series, and in this episode we will be covering one of the more important concepts for an introductory physics game physics course. So we're going to be going over the separating axis theorem today, which is going to help us detect collisions between axis aligned boxes and other axis line boxes and axis line boxes and rotated boxes. The separating axis theorem can also be used in more advanced collision detection though, such as detecting whether arbitrarily convex shaped objects are colliding with each other. So you can use this for quite a few things because it is a general algorithm. Typically people will use the GJK algorithm, the Gilbert-Kearthy algorithm, but that's a little bit more advanced, and so we're just going to be starting with the SAT for now, or separating axis theorem. Okay, so let's look at how this works and then we will go ahead and code it. All right, the separating axis theorem. What is this and how does it work? Well, this is actually pretty simple in concept. What it states is if you can find at least one axis that separates two objects, those objects are not colliding. That's all it is. The hard part in solving this is finding which axis is the axis that they do not collide on. So which axes do you test? And by axis, I just mean like a vector pointing in a direction. So that's an axis, that's an axis, that's an axis. They could be pointing in any direction you want. And we just have to find one line that can cut through the objects. If you can find one line that cuts through the objects, then you know they're not colliding, right? Because you can separate them. Hence, separating axis theorem. So if you're looking at this picture, you're like, well, it's pretty clear which line separates them. We can draw a vertical line right here that separates them. But how do we intuitively know that? And the way we intuitively know that is because we see that this box is aligned with the axis. We'll call this the x-axis starting at 0, 0, and it just goes right. Right, we know this box is vertical and horizontal, so it's not rotated. And then this box is rotated, and we can clearly tell that if we draw a line parallel to this box, it won't hit the box, so then we know that it actually separates these two. And so that right there is the key. You use the box's axes and this box's axes to determine whether the objects are intersecting. Now let's take this back a step and just deal with two regular boxes because it's a little bit easier to see exactly how this works. Now, how do we know that these two are not colliding? Actually, I'm going to make this a little bit more complicated too, and we'll do this. That's not a box. Okay, so we clearly know that these two things are not colliding, but how do we know that? Because if we look at it from, if we were looking at it directly from just this side, you would say, oh, well, technically they are colliding on the x-axis, right? If I draw a line, there is no vertical line I can draw that separates these two. So they're colliding on one axis, but I can draw it there. And the way we can tell that is by checking the interval. So we can check and see if they're colliding on the x-axis simply by doing this. We get all of their points, and then we sort of just throw them down onto the axis that we're testing. So then this would go here, this one would go here, and this one would go here. And then we'll call this min of A. So A's min, this is A, this is B. This is A's max, B's min, and B's max. And the way we can tell that these two are colliding is because if we look at it, we see, oh, well, this guy's minimum is less than this guy's maximum. So they're colliding right here. But we also have to make sure that his minimum is also less than his maximum, because if not, then we would have a scenario which it's actually something like this, where, yeah, technically his minimum is less than his maximum, but he's also all the way over here. So there's two things that we need to check. We need to check and see if the first box will talk from A's point of view. We need to check and see if his maximum is greater than B's minimum, so the left box, and we need to make sure that A's minimum is less than B's maximum. So B's minimum less than A's maximum, A's minimum less than B's maximum. If all that is true, we have a collision on an interval. And then if we were to do this on the y interval, so if I were to draw this up, we would see that if we project these, this is the min, this is the max, this is the min, this is the max, And clearly, these two are not colliding because A's max is less than B's min, and A's min is less than B's max. So there is no collision in that scenario because we found at least one axis where they are not separating. Now, which axis do we separate again? Well, we just separate each axis of the boxes. If any one of these axes have no collision, these four axes, like if we can find a line that we draw parallel to one of these, then there is there is a separating axis. There is no collision. So we just test each one of these four axes and then we're done. Now, the case of rotation is a little bit more difficult. How do you project the rotation? Specifically, how do you find out where this guy's min and max on this line is, right? Because that's kind of weird to think about. Well, we already know how to do this. We've done it before, right? This is just projection. It's projection. We're projecting the point onto an axis. So let's say that we want to test these two guys on this x-axis. And so x-axis, once again, is just 1, 0, the vector. So let's say we have points A, B, C, and D on this first box. How do we figure out which point is the minimum and which point is the maximum? I mean, clearly, we know A is the minimum, D is the maximum. We can just see that. But the way we programmatically find that is we'll just project each point in line. So we'll project A, put him down here, then we'll project B, then we'll project C. They'll both be right around here. Then we'll eventually project D onto the line. And we will find, we'll keep track of which one of these is the minimum, because these will all be returning just a value, right? This will just be the value of the distance along this line, the distance along this line. And then whichever one is the smallest value is the minimum, whichever one is the largest is the maximum. So we'll just loop through all the vertices and try and look for the minimum and the maximum. And then for this one, since we are testing his axis, we clearly don't have to do anything special. He is aligned with the axis, so we just use his minimum, which will be this point, and his maximum, which will be this point, and we just use the x values there, and then we will have this point and this point. Now, last step. I mean, it looks pretty easy to project, right? You just draw a line straight down. That's all it is. But this doesn't relate mathematically. How does this actually work? And there is one shortcut we can use. If we draw the vector, this is A's vector, right? A's vector just looks like a point from 0, 0 to wherever the point A is. And it has some theta with which it hits the x-axis. We'll call this x. The x vector looks something like this, right? It's a unit vector. It's length 1, and it's just pointing in the x direction. Well, what do we know about this? This looks like a triangle, right? And what are we looking for? We're looking for this length right here, which we'll call d, the distance. Well, that distance isn't too hard, right? This is actually just, d is just the magnitude of a, so this whole vector is a. So the magnitude of a sine or cosine theta, right? This is just magnitude of a cosine theta. Just trigonometry, right? But what is theta? How do we find theta? We have that handy function, right? The dot product. If we do a dot x, that ends up giving us the magnitude of a times the magnitude of x times cosine theta. That looks super familiar, right? So not only is this the same theta, but also look at this. What is d? D is a cosine theta. We have an a, we have cosine theta here. We almost have the whole thing. The only thing bothering me is this x, because that could throw everything off. But 1 second, x is a unit vector, which means that the magnitude of x is equal to 1. And 1 times anything is just itself. Therefore, we can say a dot x is also equal to the magnitude of a times cosine theta, which just so happens to be d. So, long story short, how do we find the projection of these points onto the axis we're looking at? Well, since each axis is going to be a unit vector, we can literally just do the point dot the axis, which gives us our projection, our value. So yeah, we'll just do that. We'll say a dot x, then we would do c dot x, then b dot x, d dot x, and that would give us our values. We loop through those, find the minimum and the maximum, and then we create an interval with those, which we would say some interval, which is really just going to be a for the min and d for the max. And then we continue And then we would check, like we said, is this guy's maximum less than his minimum, and is his minimum less than his maximum? If all that is true, we have a collision on this axis. We move on to the next axis, which would be something like this. And then we would do the same thing. We would just figure out, okay, project all the points onto that axis and see if it's colliding, and so on and so forth, until you either find an axis where they are separated, which means there is no collision, or you finish all the axes and they collide on every single one, which means you had a successful collision. With all that down, let's code this. I am inside of our intersection detector 2D. I'm going to go ahead, copy this real quick, scroll all the way down, and paste it right here. We are going to be doing AABB versus primitive tests. So the first one that we would like to do is public static and Boolean. So I'm just going to copy this because we want to make all our methods look very similar. So we'll say this is actually going to be our AABB and circle, and then we'll just say return circle and AABB, and then we'll pass in the circle and the box. So just overload this method real quick so that we have that, and then we're going to change this to AABB, and then I'm going to move all that just over to here. All right, so that we have the overloaded method. Copy and paste that, and this will be our AABB and AABB. So if we have two AABBs, how do we check if they're colliding? Well, like I said, we can use the separating axis theorem. And we're going to need a few helper functions for this, okay? First one being, we're going to call this private static vector2f get, oh, and I'm capitalizing these. I think these functions should be capitalized since it's like the name of a class here. You could lowercase this if you want to. I'm just thinking about naming conventions. I've been writing in C++ and I typically capitalize, but in Java, function names are typically started with lowercase. So whatever your preference is, you can change this if you'd like. Okay, anyways, but we're going to need this function get interval, which will return, like I said, the minimum and the maximum of a box on an axis, right? So what are we going to take in? We're going to take in an AABB. We're going to call this our rectangle. And we will take in a vector 2f, and this will be the axis on which we want to get the interval for. Now, I'm going to start this, and then I want you guys to try and finish it yourself. So we're going to say vector 2f result. So the result is literally just going to be a vector where the x value is the minimum of the rectangle on the axis and the y value is the maximum on that axis, just like we did in the math. Then I'm going to say vector 2f min equals rectangle.getMin, and then vector 2f max equals rectangle.getMax. Okay, and then the next thing we can do is we can get a pair of all those vertices. So we'll say vertices equals, and we're just going to create an array. And we're going to do this very similar to how we did that debug drawing thing that we did the other day. So we'll just say min.x, min.y, and then we'll say new vector 2f, min.x, max.y, and then new vector 2f, max.x, min.y, and new vector 2f, max.x, max.y. So this will get us a pair of all the vertices. You can think of this like binary, right? 0, 1, or 0, 0, 0, 1, 1, 0, 1, 1. So that gets us all of our vertices. Now what I want you guys to do is do what we talked about. Use the projections to find which of these is our minimum and which of these is our maximum, and then store those inside of result and return result. So pause the video real quick. Try and do that based on the math that we went over, and then I'm going to do it right now. Okay, so how do you do this? Well, you just say result.min. First of all, we're going to initialize this equals, and not result.min, but result.x equals the axis dot vertices 0. And then we're just going to say result.y equals result.x. So we'll initialize both of these just to the bottom one, just so that we have them initialized. And then we're going to loop. We're going to say for int I equals 1 until I is less than 4, I plus plus. And how does this work? Well, we just say float projection equals axis dot dot, and then we want to say vertices I. So we just dot the vertice against the axis, which gives us the projection. And we'll say if projection is less than result.x, result.x equals projection. And we'll say if projection is greater than result.y, then result.y equals projection. So this is pretty simple, right? We just project each axis against each of the vertices, just like we talked about in the math, get the projection, and then we just see if the projection is greater than our current max, which is just whatever was the first axis. And then if it is, then we set this as the new max, and then if it's less, then we set it as the new min. We're just finding the max and the min. And then we return it. Now we can project an AABB against any axis, which works quite well. Now let's create one more helper function for ourselves. We will call this private static Boolean overlap on axis, and this will take in an AABB. We'll call this B1 for box 1 and AABB. We'll call this B2, and then we'll say vector 2F, and this is the axis we're testing against. So this should return whether box 1 and box 2 overlap on this axis. Now remember, we need to get the interval for box 1, the interval for box 2, and then how do we check and see if those are overlapping? I said there was 2 conditions. Try and code this yourself real quick. Go. Okay, so how would I code this? Well, we already have our helper function, which should help us out somewhat. So what we'll do is we will say vector 2f interval 1 equals get interval, and we're going to give it b1 in the axis. We'll say vector 2f interval 2 equals get interval b2 in the axis. And note of clarification, when we get the axis, we're expecting this to be normalized. If it is not normalized, that is an error on the user of this functions part. It's going to return the wrong result. So good thing to keep that in mind. Then we return interval 2 dot x is less than or equal to interval 1 dot y. So interval 2 x is the min. So is interval 2's min less than interval 1's max, and is interval 1's x, which is the min, less than or equal to interval 2's max, which is the y. And we just return that, and that will tell us whether these 2 boxes are colliding on this axis. We almost have our full function done, right? We have a way to check and see if it's overlapping on an axis. Now we just need to check and see if they are overlapping on any of their shared axes. Well, how do we do that? So we have 2 AABBs. Remember AABB axis aligned, which means that they are aligned on the 1, 0 axis and on the 0, 1 axis, the x and the y axes. So those are the only axes we have to test for this. So what we're going to do is we're going to say vector 2f axes to test, and this is an array, equals, and then we'll just say new vector 2f 0, 1 and new vector 2f 1, 0. Right? And so this will give us an array which stores each of the axes we need to test, and those are unit axes. Next, what are we going to do? Well, we're just going to say for int I equals 0 to I is less than axes to test.length I plus plus. If overlap on axis b1, b2, and the axis is axes to test I. Actually, we're going to say if not, return false. So if we find one axis which they're not overlapping on, they are not colliding at all, we return false, exit early. Otherwise, if we complete that loop and it hit true on every single one, we return true because we had a successful collision. And I'm going to copy this real quick and block off this code and just say SAT helpers, just so that we know what those are. That's not too bad, right? This is the separating axis theorem can look super confusing, but once you get down to the root, it's actually not too bad of a function. Let's go ahead real quick and we'll say public static Boolean AABB and box 2D. And we'll take an AABB, we'll call that B1, box 2D, we'll call that B2. And then we're going to just overload this method real quick because we do want this to work for box 2Ds as well. So instead of taking rect, we'll do this, and then we literally just need to change the vertices. We'll say instead of it equals this, it is just equals the rect.get vertices, and then we can get rid of these, and the rest of it should work exactly the same, right? So now we can overload our overlap on axis function too to take in a box 2D and an AABB should work the same, and then we can overload it one more time to take in 2 box 2Ds. And that should cover all of our cases. So now we have overlap on axis for every combination. We have get interval for every combination, which means we should be able to do pretty much the exact same thing. The only thing now is to figure out which axes you need to test. Remember, I said it was going to be the axes of, 0, 1, and 1, 0 because we have an axis line box. But then how do you get the axes of the box 2D? Go ahead and try that yourself real quick. See if you can figure it out. Okay, so how the heck did I solve this? Well, we have a handy rotation function that we can use. So the way I solved this was I actually just said vector to f axes to test equals, and then we're going to say new vector to f 0, 1, new vector to f 1, 0, of course, because those are the axis line boxes. Then I'm going to go ahead and just say new vector to f 0, 1, new vector to f 1, 0. But don't worry, we're not just going to leave it like this. And I'm going to format this so that's a little bit nicer. And we need to make this an array, of course. So this isn't currently the correct axes, right? Because these are just two duplicates. So what we need to do is we need to rotate these. So these are basically like the unrotated box, right? The unrotated axis line version of this box 2D. Now what we need to do is rotate these according to his rotation, and then it'll work fine. So we'll just say jmath.rotate. And we want to rotate axes to test 2. Wait, yeah, 0, 1, 2, and 3. Those are the ones we want to rotate. And we want to rotate it about b2.getCenter or get rigid body. We need to change this too. Get position. And we want to rotate that. Oh, it was degrees. How many degrees we want to rotate it, and then that. So we'll say how many degrees we want to do get rigid body.get rotation, and we want to rotate it about the box's center. We can copy this, paste it, and then we also want to rotate axis 3 around the same exact thing. And what that will end up doing is it'll basically take, think about it as if you had an L and you just rotated that L so that it fits the box again. And now we have the correct axes. Then we can copy this. Well, not that part, but this. Hey, we have a working function. Now, of course, I have not tested this yet. I have not written unit tests. I would highly recommend you work out some concrete problems or write some unit tests. Make sure I didn't make a stupid error, and then we can make sure that this all works correctly. But that has been the separating axis theorem. Once again, when I first saw this, I thought it was very difficult because I did not have somebody who could explain just how it's not really that bad. Once you see the math and how the math just sort of works out, you can see it's just intuition with a little bit of some math jujitsu. But yeah, I hope you guys enjoyed this. If you did, please hit like and subscribe, and stay tuned for the next episode in the physics tutorial, in which we will extend this for our box 2Ds to check and see whether box 2D is colliding. And you can actually try and implement those yourself because we're going to be using the separating axis theorem once again. I'll see you guys then. Thanks.